Hi everybody, welcome to Mrs. John's lesson. This is for year 13 physics and this is lesson 3 on DC and capacitors, and today we are looking at the concept of internal resistance. So what does this all have to do with? This has to do with batteries. Okay, now the thing is, batteries that supply electrical energy are actually made up of chemicals. So there's electrolytes and electrodes in them. And the thing is, the chemicals within the battery use up some of the energy that the batteries provide. And when you have a battery and you look at the battery, you go and buy a battery like this particular one is a 1.5 volt battery. Okay, so that's what, so this whatever is written here is what's called the claimed voltage of the battery, and the claimed voltage of the battery is actually called the EMF of the battery, and the symbol for EMF is actually a Greek letter, so it's written like this. So this is what's called the claimed voltage. So what else does it mean? So a battery, sorry, that's my dog with some papers. So you have the battery with a positive and negative terminal, and I'm just going to do this a little bit. Every time a coulomb of charge enters it, if it's a 1.5 volt battery, each coulomb of charge is going to get 1.5 joules of energy. So the amount of energy gained by each coulomb of charge when it enters the battery is called the EMF of the battery. Now, if you have a battery and you connect a voltmeter across it and you do nothing else, so you're trying to measure the voltage across the terminals when it's actually not supplying energy to do anything, so there's no lamp connected across it, nothing. So that voltmeter will read 1.5. So it's also the voltage across the terminals of the battery when there is no current flowing. So there are a few definitions for the term EMF. Claimed voltage, energy gained by each coulomb of charge that enters it, and also the voltage across the terminals when there's no current flowing. But when there's actually a current flowing and charges that gain that much of energy when it enters the positive terminal, so batteries have a positive and a negative terminal, so when it enters the battery they gain some energy, but not all that energy is available to the circuit outside, because the chemicals in the battery use up some of that energy. Now the chemicals within the battery have some resistance, and this resistance is what is called internal resistance. So whatever voltage is available to the outside or the external load, so this could be a lamp, could be a resistor, could be anything, the voltage that's available to the outside is what's called terminal voltage. So the symbol for internal resistance is a little r, and the symbol for terminal voltage is a capital V. So how do we get the circuit current? Now the circuit current depends on the supply voltage and the total resistance. So now if you look at this, this is a symbol for a battery with its internal resistance. We draw a dotted line over it to say that whole thing can't be separated, it's one thing. You can't remove the internal resistance from the battery because it's made up of all those chemicals that have resistance. So the circuit current depends on the total voltage, which is the EMF, the claimed voltage, the total amount of energy that each charge gets, plus the total resistance. Now the total resistance is made up of this external load and the internal resistance. So this is one way that you can write the equation, or if you rearrange this, you get internal resistance is I times R plus R, or if I factorize it, I can get internal resistance. I'm just going to lower this a bit so that you can see what I'm writing, is equal to I times R plus capital I times little r. And then that can go further. Now this I times R is what we call the terminal voltage, and the capital I times little r, that's called the voltage drop across the internal resistance. So that's the amount of energy that's lost by the internal resistance. Now just from here you can see if the current is quite large, then there's a bigger voltage drop across the internal resistance. Okay, and also the other thing is, if you have new batteries, they have a low internal resistance, whereas if you have old batteries or old cells, then the internal resistance increases, so the lamps are not going to be very bright because the terminal voltage becomes quite low and there's not enough energy to light your regular lamps. Okay, so I'm just going to, there is an experiment that we do to show all this, and I'm just going to rub this board. It's quite dirty. Okay, it's a bit better now. All right, okay. So the experiment that we do is, we can take a battery, you can take a power pack, it works with both of them. So say you've got your power pack and you've got an emitter and you've got a rheostat which you can use to change the current. And you also need, so you need to measure current, you need to measure voltage, and we're going to measure the voltage across the source here, okay, for differing. So why is the rheostat is there, so that you can move the slider to get different amounts of currents. And then what we do is we gather data of voltage across the terminals of the battery when there's a current flowing, or that's your terminal voltage for different currents. And then what you notice is, if you plot a graph of terminal voltage measured in volts against currents that's measured in amps, you will see that as current increases, the terminal voltage decreases. So you actually get a graph with a slope like this. It has a negative gradient. Now, you know the equation for a straight line. So the equation for a straight line graph is y equals mx plus c. Okay, now here y is your v. Okay, m is the gradient. So that's whatever the gradient is. And x is the quantity on the x-axis, which is times I, plus an intercept. Now you'll notice that your intercept on your y-axis is actually the EMF. And you will notice that the gradient of this graph is actually the internal resistance. So if you're given a graph like this, one way to calculate internal resistance is find the gradient of the graph. Okay, so I hope that made sense. Bye for now.